This is a typical gaseous equilibrium problem that you're going to have to calculate on the AP exam. So if we take a look at it, we start looking, if you notice a couple things, when I read the problem, one of the things we focus on is what is at equilibrium and what is initial. So they tell you heated hydrogen sulfide gas decomposes according to the equation above. They tell you if 3.40 grams of H2S is introduced into a 1.25 liter container. So that's telling you what's going to be the start of the reaction. If you read a little farther, you see this. And 3.72 times 10 to the negative second moles of S2 is present at equilibrium. What that's telling you is this would be your E line value, and the yellow would be your I line value when you go to make a ice table. So remember, we care in AP, you're really paying attention to what's the I line, what's the E line. So if we look here, so we take this problem right here, so we're going to go, get rid of that. Let's see here, move out there. So when I look at this, the first thing they ask me to do is they ask me to write an equilibrium expression. So that's easy, it's products over reactants, so I'm going to just say S2 to the first, H2 to the second, products over reactants, and then H2S, and I square that sucker, is equal to Kc. So you get 1 point on the exam for writing the equilibrium expression. The next part, part B, they want us to calculate the equilibrium concentration. So if they want us to calculate the equilibrium concentration, we have to make an ice table. So what we're going to do to make the ice table is we're going to start with the reaction. So we're going to go 2H2S, double arrow, you're going to get 2H2 plus S2. And then, remember, I is initial, C is change, E is going to represent equilibrium. So the first thing we have to go back and is figure out what our initial value is. Well, they tell me I have 3.50 grams of H2SO2 in 1.25 liters. So I have to turn that into molarity. So I would take 3.40 grams of H2S, divide by the molar mass of H2S, which is 34 grams, of H2S equals 1 mole. I am going to get 0.100 moles, 3 significant figures going in, 3 significant figures coming out. So I'm going to get 0.100 moles. But I need molarity, because either molarity or atmospheres are the only two things that can go on the ice table. So I'm going to take 0.100 moles divided into 1.25 liters. That will give me a molarity of 0.0800, again 3 sig figs. That's my initial molarity of H2S. So then I'm going to go down to my ice table and fill this in, 0.0800. At the start, they don't mention any of this, which is 0 or this. Do a little algebra. This is going to be 2x, 2x, and then plus x. This is minus because, remember, the reaction is always going to go towards the 0 side. This will be plus 2x and plus x. The next step is I am going to drop it all the way down. So I'm going to get 0.0800 minus 2x, 2x, and x. Now, in order to calculate equilibrium, I need 3 equilibrium values. In fact, that's where they're asking us to solve. If it is a molarity problem, they will give you a way of finding x. In fact, they gave us this right here. If we look, right here it says 3.72 moles of S2 is present at equilibrium. So what does that mean? If I have 3.72 moles present at equilibrium to the negative second, I would basically go 0.0372 divided by 1.25, and I get basically 0.0298 for 2 significant figures. So what I do is I take 3.72 times 10 to the negative second moles divided by 1.25 liters, which will give me a molarity of 0.0298. That's my molarity. So what that means, when I come down here, they're giving me this value. 0.0298 represents that. If I multiply that, if I take 0.0298 and I multiply that times 2, I end up with 0.0596 for this value. And then I would plug in x in this one, so I would go 0.0800 minus 0.0596. This is going to be equal to 0.0204. So all I did was take, so now what I've done is I found all my equilibrium values. If you look at the problem, what they ask us, part 2 of the problem was they want you to calculate the equilibrium concentration of H2 and H2S. So my answers are, for that on the exam, I would have that molarity right there and that molarity there. Since I have all 3 values, the next thing they asked me to do is calculate the value of Kc. Well, remember the expression we did at the beginning was what? H2 was H2 squared S to the first, S2 to the first, over H2S squared, right? What I'm going to do is take my values from the previous page, the values from the previous page, which are right here. I go here, what did I get? I have the values I have, let's see here. I have 0.0240, 0.0596, and 0.0298. So when I go over here, I'm going to take the S2 was 0.0298. So that's going to be 0.0298, and that'll be to the first. I'll take 0.0596. I'm going to square that because it's squared, and then I take the bottom, which I believe was 0.0204, and I am going to square that. And I'm going to pop that in a calculator and do the math. You're going to get somewhere around 0.250, somewhere right around there. I just kind of ballparked it. But you're going to get 0.250 at that point. That will be your Kc. So that will represent your Kc. Just put it in the expression. When I do the math, I get 0.250, somewhere right around there. Depends on your rounding, how you rounded them off. Maybe it could be a little different. The next part of the problem asks me to find the partial pressure of S2. Whenever a gas is not at STP in the AP exam, we're always going to use PivNert to find the pressure of a gas, especially if it's a gaseous equilibrium problem. They're going to ask you for the pressure of a gas. It's pretty much what they always do. So really, P is going to be equal to NRTV, NRT divided by V. So what do? Well, I need moles of S2, but wait, if I go back to the original part of the problem, look what I have highlighted there. They provided me with 3.72 times 10 to the negative second moles. So I'm going to come over here, and my moles are going to be 3.72 times 10 to the negative second, goes there. My R is going to be 0.0821 liters, atmospheres, moles, Kelvin. And then finally, temperature, 483. So I'm going to plug in 483 Kelvin right there. And then on the bottom, my volume. Well, the volume in this, they told you was 1.25 earlier. Earlier in the problem, it's 1.25. You plug it all in, you are going to get a pressure of 1.1 ATM. So it's going to be equal to D. The correct answer is 1.18 ATM. Remember, if they ask you for pressure in a gaseous equilibrium problem, you're going to just use PivNert. The last question is asking about reaction flipping. If you think about it, if you look at this reaction here is very similar. Let's go to the first page where the problem was. They always do this on the exam. They provide you this reaction, but if you look down here at the bottom of the page, these two are related to each other. Remember, we talked about reaction flipping, right? We find the Kc for this up here to be equal to Kc for this. When we did the math, we found that equal to be somewhere around 0.250, right? Well, what's the difference between this equation and that equation? The first thing is it's been flipped, because you see how H2S is here and now it's here. So what do we do to K if we flip it? Well, we take the inverse. So that would be equal to 1 over 0.250 would be the first thing. But then I check the coefficients. The coefficients here of H2S is 1, or actually 2. The coefficient there is 1. So what's happened is it's been multiplied by 1/2. When we multiply anything in an equation, we raise it to that exponential power. So you take 1 over 0.250, and then you would raise it to the 1/2 power, which is the exact same thing as the square root. So what you would end up with is 1 over 0.250. You take the root of it, and I believe that's going to be somewhere around 2. I think that if you plug that into your calculator, it'll be somewhere around 2.0. It'll be close, 1 point something right there. Sig fig wise, if you calculate 3 sig figs here, you should have the answer at 3 sig figs there. So you take, actually, let me do it on the calculator. Yeah, it's going to come out to be 2.00. That is a typical gaseous equilibrium problem. To review, key things they're going to have you do, they'll have you do a K expression, so either Kc or Kp if it's pressure. So products over reactants using the coefficients equal to K. You'll fill out an ICE table. You fill out an ICE table, you pay attention to the initial values. What are my I values? What are my E values, right? If it's a gaseous problem, we talked about this in class the other day, you would use partial pressure. The E line would equal the total partial pressure, and you would solve for X. You do that, you plug it into the expression, you get K, and then there's one of the problems you saw in this one. They asked you to find the partial pressure of a gas using PV equals nRT, and then the last part was Kc, Kp manipulation. They could have you convert from Kp to Kc using the equation, just to do a conversion. That is possible. And then we'll talk about one other thing. We'll do that next week. One other thing they can add, and that is pretty much a gaseous equilibrium problem. Hopefully you have a good day. I will see you tomorrow.